We're now going to talk about how, if I'm given 3 different points in my Cartesian plane, how I write an equation for a circle for those points. Before we work in our Cartesian plane, though, I want to talk about the actual geometric depiction that we're going to use to do this in the coordinate plane. So we're going to do some Euclidean construction right now. And this is actually part of what we would have been if we were doing a proof in Euclidean geometry, the proof that 3 non-collinear points determine a unique circle. So what we're doing is I'm going to draw 3 random points. And the first thing I'm going to do, I'll go ahead and label them, A, B, and C, is I'm going to draw 2 lines that connect all 3 points. So I'm going to connect A and B to C. So using Euclidean construction methods, I would be using from Euclid's first book, Elements, Proposition 1, that I am able to construct a straight line from any point to any point. So I'm able to construct a straight line from A to B and B to C. The next thing I'm going to do is I'm going to construct of AB, line AB and BC, I'm going to construct their perpendicular bisectors. Now normally we would do this using a compass or circles. That's how Euclidean construction would do it. But since we are going to be doing this in the Cartesian plane, I want to mimic what we're going to do when we do that using our algebra and our concept of the coordinate system. So what we're going to do first is we're going to, on each line, create a midpoint, which is where our bisecting line will go. So I'm going to construct that midpoint. And then from there, I'm going to construct the perpendicular bisector. So if we're in our coordinate system, we're going to do that by finding the slope of this line and then taking its reciprocal and multiplying that reciprocal by -1. And then I'm going to fit a line with that new slope, that perpendicular slope, at this midpoint. So I'm going to go ahead and construct the perpendicular line here. So I need to click on both of those. And if I were doing Euclidean construction, again, I would use circles to find those perpendicular bisectors. And Euclideans, again, is Elements, Book 1, Proposition 10, will say that I can bisect any given finite straight line. So I've got a straight line here that has ends to it. It's not infinite, so I can create a midpoint of it, and then I can bisect it. So now I'm going to find the intersection of these 2 lines, which is right here. And Euclidean construction would tell me through postulate 3, so original thing that he wrote in book 1, that I can now describe a circle or make a circle out of any center and radius. So what I've just constructed is my center point. So this bisector right here, or this intersection right here, is going to be my center point. And as we already knew, these 3 points were going to be on the edges of my circle. So any of these 3 points from my center point are going to be my radius. So now I can use my circle tool, and I can start from my center, and I can go to any of these points, and they're all going to have the same radius, and I have now constructed a circle out of just 3 points. So geometrically, if we're using Euclidean construction, this is how we did it. Now let's translate that to our Cartesian and coordinate plane and actually work a problem as an example. So now we are going to use our Cartesian plane, and we are going to create a circle from the points 3, 3, 7, 1, and 6, -6. From the geometric proof, if you'll remember, the first thing that we did is we drew 2 lines that connected all 3 of these points. So I'm just going to show you those lines. We're not actually going to calculate the equations for those lines because all we need from them is the slope, because remember, we're trying to find the midpoints and then from those midpoints create a perpendicular line from these. So we just need the slope to do that. So let's go ahead and do those calculations. So now I'm going to work algebraically, and I'm going to, as you see, I have my 3 points listed here: 3, 3, 6, -6, 7, 1. I'm going to work with the points 3, 3, and 6, -6 first. So the first thing we need to do is figure out what the slope is and what the midpoint is, because what we are going to do is we're going to create at that midpoint the perpendicular bisector. So we'll start with the slope. I calculated the slope of the line that is between these 2 points, and that's at -3. So the slope of the line that we want to draw for that perpendicular bisector is going to be positive 1/3, because it's going to be the reciprocal and the negative value of that reciprocal of this -3 slope. Now we need to find the midpoint by averaging our x values and our y values. So if I do that, I find that my midpoint of this line is at 9/2 and -3/2. So let's look at those calculations that we just did. I already drew the line, but let's go ahead and draw in that midpoint at 9/2 and -3/2. So you see there it correctly creates the midpoint between these two lines. Now let's work on finding the slope and the midpoint of this line over here. So if I work on finding the slope between 3, 3, and 7, 1, and I go ahead and do that calculation, I'm going to find that the slope is -1/2. So the new line, or the perpendicular bisector between these 2 points that we want to create, is at the midpoint, and it's going to have a slope of its negative reciprocal. So it's actually going to have a slope of positive 2/1, or just 2. And then if we find the midpoint by averaging our x values and our y values, we're going to find our midpoint is at 5 and 2. So again, let's go back and look at our depiction in Desmos. So we said the slope of this line is at -1/2. So if I go down 1 and over 2, you can see that looks to be the accurate slope. And then if I find the midpoint at 5, 2, you can see that we have the appropriate midpoint. So we've completed our first Euclidean construction step here so far, as at least drawing the segments or the line segments between them and finding the midpoints of them. Now let's calculate the equation of the line of the perpendicular bisectors of each of these, the lines between these points. So if I start with this, remember our starting point for our perpendicular bisector is that we had a slope of the line between these 2 points at -3. So if I take the opposite of the reciprocal of this value, I get 1/3 as my slope. So now I need to find at this midpoint of 9, 2, and -3, 2, a line with a slope of -1/3. So I'm going to use substitution with this midpoint in my equation. So I substitute that -3/2 in for y, and that 9/2 in value for x. And if I solve for b, I get b equals -3. So my equation of this line is y equals 1/3 x minus 3. So let's take a look and make sure that that is the perpendicular bisector. So we just said it was y equals 1/3 x minus 3. So you can see my red line drawn here. That looks like a beautiful perpendicular bisector. So let's go ahead and calculate the other one. So if I begin to calculate my perpendicular bisector, remember the slope of the line has to be the opposite of the reciprocal of the slope between these two lines. So it's going to be 2, as we said. So y equals 2x plus b. If I use my midpoint as my substitution point, because I know that's a solution on this line, I get 2 equals 2 times 5 plus b, and therefore b equals -8. So the equation of this line is y equals 2x minus 8. So let's look at that and make sure that's correct. So again, we keep adding things onto this. So if I go ahead and graph y equals 2x minus 8, you will see that I have a perpendicular bisector. Now, we know by looking at this graph that these lines are going to intersect at the points 3 and -2, but since we're solving algebraically, let's go ahead and figure out how that has to be done. So if I'm trying to find the intersection of two lines, I need to solve the linear system of equations. So let's go ahead and do that. So now I have a system of linear equations where I have my one perpendicular bisector of y equals 2x minus 8, and my other one of y equals 1/3 x minus 3. So to solve for these, I am going to use substitution because I can set these two equations equal to each other because y equals y. So by substitution, I can say 2x minus 8 is equal to 1/3 x minus 3. If I add 8 to both sides, I get 2x equals 1/3 x plus 5, and if I subtract 1/3 from each side, I get 5/3 x equals 5. And if I solve that for x, I get that x equals 3. Now to solve for y, I'm going to take one of these equations. I'm going to take y equals 2x minus 8 in this case, and I'm going to place that and substitute that x equals 3 back in. So I'm going to get y equals 2 times 3 minus 8, and therefore y equals -2, which is the point 3, -2 where they intersect. So let's go look at that point. So I'm back to my drawing, which keeps getting messier and messier because I keep adding things. So if I look at the point 3, -2, and I put that on here in Desmos, you will see that that point comes up. It is the intersection of those 2 points, and that is going to be the center of my circle. So now we have the center, and we're almost there. We are almost there with our formula. We just need to figure out the radius. So we need to use the distance formula between this 3, -2 and one of these points, and then we will find the radius of this particular circle. I'm going to use this nice point of 3, 3, and 3, -2 because that's a really easy one to calculate the distance formula with, since it is a straight line. So let's go finish this step, and then we can write the equation for the circle. So as we said, we are trying to find the distance between the point 3, 3 and 3, -2, and you probably already know it, but let's go ahead and run the distance formula just so we know it. So the distance formula says take the square root of the addition of delta x squared plus delta y squared. So if we calculate that, we are taking the square root of 3 minus 3 squared plus -2 minus 3 squared, which is 0, technically 0 squared, which is 0, plus 5 squared. The square root of 5 squared is 5. So we know that our radius of this circle is 5. So now if we use our circle formula for x minus h squared plus y minus k, where h and k are the center of the circle, and r squared is our radius squared, our center of the circle was at 3, -2. So our circle equation is going to be x minus 3 squared plus y plus 2, because we had a -2 here, squared, and then our 5 squared, which is 25. So let's go ahead and graph it and see if our solution works. Okay, so you'll see here that I've entered in the solution we just found of x minus 3 squared plus y plus 2 squared equals 25. And if I go ahead and graph that, you will see that that circle fits those 3 points we set out to fit. So we just used Euclidean construction and his axioms and postulates from his Elements book to transfer and create the idea that in our coordinate plane we can use those geometrical depictions and constructions to also take any 3 points and create a circle around them. So now you can practice this as well. It's quite a long process, but it's a pretty cool process that we can do that now.